Hi, and welcome to my Lab 5. This is the code I have for Lab 5. All I'm doing is reading the two analog signals. Then I'm using the potentiometer signal to create a frequency, a sampling frequency, changing that to a time, then using that time as a delay. Then I'm sending the Nscope signal to the processing IDE using Printline, and this is what comes up. I can change the potentiometer now, and you can see the sampling changes. And here are my results when I changed the fundamental frequency and the sampling frequency. I found that there was aliasing whenever the sampling frequency was less than double of the fundamental frequency. So I have down here that for 75 hertz, there was aliasing when the sampling was 100 and 140 hertz. For the 100 hertz, I found that there was aliasing when the sampling was 100 hertz, 148 hertz, and 215 hertz. The last one is probably because of the actual sampling frequency was more like 184 hertz, I believe. And for both 250 hertz and 300 hertz, there was aliasing for every sampling. And as you can see, if you move down here, you can see I've shown an example of how I calculated my theoretical aliasing frequency. So what I did was divided by the sampling by 2 to get the Nyquist frequency. Then I divided the fundamental frequency by the Nyquist to get this number. If that number was more than 2, or I'm sorry, less than 2, I would subtract 2 from that number to get the decimal of what the actual aliasing frequency is. And I can show you this table where I found all the theoretical and I plugged in all the experimental aliasing frequencies. And as I said earlier, whenever there is a sampling frequency that is less than double of the fundamental frequency, there is aliasing, which was proven correct by the experiment. The circuit has changed a bit. So before it was connected to A1, now it's connected to P1 so that we can get square waves, and this is what we get from processing. Now the circuit is back to how it was before, and we get these results for the triangular waves. So the reason that the graph looks like this is because, especially for the square wave, since it's a combination of different sine waves put together, we see the fundamental frequency, that's the first one over here, has the highest influence on how the square wave looks. Then the next one is when the first harmonic, the second harmonic, and so on and so forth. And you can see that each of them have a little bit less influence on why the square wave looks like this. So we're seeing the different frequencies that are making the square wave. Same can be said about the triangular wave, but almost to a lesser degree. You can see that the fundamental frequency has the highest say as to why the wave looks like that, but we can see that as the first harmonic, second harmonic, you can even kind of see the third harmonic as you go on, have a little bit of a say. However, because the triangular wave kind of looks like a regular sine wave, you don't need that much of an influence by the other non-fundamental frequencies.